Good morning, everybody. This is the second part of how to customize kind of a hello world example of how to fully customize and replace the O3DE render pipeline. But in this case, the first part of the presentation, as a quick recap, we replaced the main render pipeline without writing C++ code, exclusively mostly writing shader code, and that's it. And we were able to replace what, if you look on the left top square here in this presentation, that is how the default scene renders with the main pipeline. And after applying a material that we created to the ground plane, the shader ball, and of course we have a pipeline that doesn't have a skybox, then on the bottom right, we can see how it looks like. So at the end of the day, you are able to add as many meshes as you want and render with the custom shader. So that's what we learned without writing C++, which is very important, because a lot of people think that to even replace the render pipeline, you need to write C++, and that's not right. So this shows you how flexible the engine is from the point of view of data driving the engine. So this part is, okay, so now we need to write C++ because we want to achieve more. And basically, the first part of writing C++ is the concept, is going to help us in one thing. In the first part of the presentation, we had to copy all of the what is called the path template a file that comes with the renderer, copy into our project. And by customizing that and making a copy, we were able to add our new custom passes. And that's kind of a drag because you have to copy paste things around and add your passes to a file. But the only benefit of that is that you don't have to write C++. But with C++, there is a more elegant way than copy pasting the original set of pass templates. In this case, you're going to register, and everything is detailed here. And of course, as most of you know, there is already a GitHub project where this custom application is there, so you can see it all working in there. But suffice to say, there is an API when let's say, typically your system component starts, you connect to an event handler that notifies you whenever the engine is ready to consume your list of new pass templates. And here is an example where basically at the bottom here, there is a function called load pass template mappings. And I specified the path to the custom is a small file where we're going to list the passes we're adding to the engine. So in this case, it's a little bit of C++ code, but now you have more flexibility and you don't have to copy paste files around. So all of this is already on GitHub, so you can see the details of how it all works. So this is the first part of when C++ is needed. It's basically, if you need to add more pass templates, you have to somehow connect to that event handler, and the only way to do it is through C++. Now, furthermore, what else do you need C++ for in terms of customizing the render pipeline? So typically, let's say the philosophy of the render pipeline is that you have some data. That data eventually is exposed to the user through a C++ component. That C++ component feeds data into a feature processor, let's say typically the mesh feature processor. So you have data as assets. There is a mesh component. The mesh component gives that data to the feature processor. The feature processor generates draw packets from from that data. And eventually those draw packets are distributed across all of the raster passes in the pipeline, in whatever is the current pipeline. Similarly, you can have a component, a feature processor that doesn't generate draw packets, but definitely knows of the existence of a specific passes and feeds some custom data to those passes, and those passes is your custom C++ code. connects everything and figures out what or where to render. Like a classical case is, for example, doing volumetric rendering or any other effect that doesn't match the archetype of using draw packets. So that this also means that if you have to have custom passes, then of course you have to write custom C++ classes. And then there is an API that I mentioned at the bottom where, for example, in this API, there is a pass factory add core passes. If you follow that API, you're gonna see how the engine registers all of the passes that ship with the renderer. Similarly, for example, another interesting case where you can write C++ code without dealing much with the renderer is when you want to leverage the mesh feature processor. So typically, the mesh feature processor assumes there are mesh assets and also material assets. You instantiate a mesh component and a material component. That's how you configure your character or whatever. And all of this data is fed to the mesh feature processor, which eventually generates draw packets out of it and it renders. Alternatively, you can actually leverage the mesh feature processor itself and you can create your custom meshes. For example, let's say you wanna create a client server application where you have a TCP server in the cloud generating meshes on the fly, and you have the O3DE engine as a client connecting to the TCP stream, and of course you will have to create a custom C++ component to convert all of that TCP data into mesh data that the mesh feature processor can consume. So that's another interesting case of where C++ you will have to write, but it's mostly in this case, you're just writing C++ code and there is no shader code that you have to write and so on, but you're leveraging the mesh feature processor. In the code today in the engine, if you look at the white box gem, the white box gem is a great example of a gem that leverages the mesh feature processor by creating custom meshes on the fly. Basically, when you are creating what is called, gray boxing or white boxing your scene with a simple geometry to define, hey, here is a building, here is, a prop. All of those meshes are created on the fly and leverage the mesh feature processor for rendering. And of course, other cases where you're going to need C++, imagine you need to feed real-time data that feeds into your shader, like, for example, the game time. There is no way today to just feed, for example, the time, by default, the engine feeds you the time. So if you want to use the scene srg m time, you can access that in your shader, and that works. But if you need to feed other kind of real-time data, of course, you need to write C++ for those things. So that gives you like an overview of, okay, all of the cases where you want to write C++. Now we're going to do a case where we're going to extend the main pipeline and we're going to add a custom feature processor. And this feature processor is going to render stickers because everybody loves stickers, right? So what we're going to see now is that you can see on the screen, on the right side, you're going to see the scene being rendered with the previous pipeline, but now there is 3 stickers, one on the bottom left that has kind of the SIGGRAPH logo, the O3DE logo, and the Linux Foundation logo. And you can, there will be components, so you can pick the location where these stickers are going to be placed, and of course the texture asset that is going to be used. So let's walk through all of that. So this is how it's going to look in the editor. Once everything is done, you're going to find that you're going to create a sticker component where you define the position, X, Y, width, and height, and the image asset. and also a checkbox that preserves the proportion of the original image asset. And then you're gonna see that, oh, we have 3 entities, each entity with a sticker component, and each one loading its own texture and pasting it in the right location in the screen per the data configured in each component. So that's kind of shows you the end goal of this. So the sticker feature processor. So the purpose of the processor is to render an arbitrary amount of images, known as stickers, overlaid on the viewport. The images can also have alpha color. The user can specify the sticker location and size using normalized coordinates, and also will preserve the original proportion of the image if needed. So this is how, a big screenshot of how the sticker processor is going to look like. So here's the data flow. On the left side, we're going to have, let's say, 3 entities or n entities. Each one of those entities will have a sticker component. Each of these sticker components, all of them, are going to talk to the same sticker feature processor. So that means the sticker feature processor is going to keep like a local map, a local database of all of the stickers is supposed to render. For each of those stickers, there's going to be a draw packet. And this draw packet is going to be given to the main camera view. And eventually the sticker pass, which is a subclass of the raster pass, is going to fetch all of the draw packets with the draw list tag sticker, and then creates the draw items that at the end of the day will be submitted as draw calls. So the sticker component is the user-facing component, and the sticker feature processor is what takes the data from the components and gives it to the renderer through this kind of normal flow. And this is the standard flow. For example, the mesh component basically works this way. There is a mesh component on the left, goes to the mesh feature processor. The mesh feature processor creates draw packets, feeds draw packets to the correct views or quote cameras. And then each pass in the pipeline fetch draw items for them based on their draw item address, also known as the draw list tag. So we're taking the same architecture and we're going to use it for our sticker feature processor. So the first thing we're going to put here is a sticker pass, which is just a vanilla raster pass. This is the asset where we're defining all we need is we don't need. So basically the render attachment configuration for this pass is that we only need a render target where we're gonna put the color. We're not even using the depth buffer. We don't care about depth, which means we're always gonna plaster on top of whatever is in the swap chain. So this is a very, as simple as it gets a raster pass definition. And of course, what truly matters is the draw list tag is called sticker. That means any draw item that has this sticker draw list tag is going to be rendered by this pass. Then the sticker pipeline pass. So in this case, it looks like in this first example, we are replacing the main pipeline altogether. We later will see at the end how to add this feature processor to the main pipeline. But for now, it's basically the same pipeline as before, where we had the pass that renders the normal vectors, and we add a second pass to the pipeline called the sticker pass. And of course, the sticker render pipeline, the render pipeline descriptor asset, where we define what is the name of the template. And this is the asset that we feed to the command line when we start the editor to say this is the main pipeline. So it's a pipeline with 2 passes. The pass that renders all of the meshes and the pass that renders all of the stickers. And here's more definition that you need to add these templates to the past templates assets. Now, interesting, remember, because we wrote C++ code the pass template is now a very tiny file with all of these 3 passes. That's it. It is not as before, where we used to have all of the passes that come with the engine, and we were adding a few passes at the end. Now we just list the passes that we are contributing to the engine, thanks to writing C++ code for that. So the sticker component controller is the liaison between the sticker component and the sticker feature processor. So when the sticker component controller is activated, it calls to the feature processor, hey, add a sticker. And each time a sticker is added, the feature processor is going to create the draw packet that represents everything that needs to be rendered about the sticker. And of course, when the component is removed, the component is deactivated, and we call the sticker feature processor to remove the sticker from their database of stickers. And if there are changes to any of these parameters that you see on the sticker component, then we're going to call update sticker geometry, or we're going to call update sticker texture, depending on what you change. So internally, each sticker within the sticker feature processor is recorded as a sticker render data. So we have the sticker properties, and based on the properties, that's where you see, this is where it gets really detailed into, how you feed data to the renderer, because you're going to need the vertex buffer view, the data for the draw SRG, and of course the draw packet. All of these data get created every time you add a new sticker. And of course, the sticker feature processor keeps a map where by entity ID, it keeps a sticker render data. And this is how a sticker looks like from the point of view of triangles. It's a primitive, like when you face the screen, it shows you the location of the ordering of the vertices 0, 1, 2, 3. And if you follow, it's right hand. So right hand, where the thumb is facing towards, coming out of the screen. And it shows you also the data in the vertex. We only have position and we have UV coordinates. That's it. And of course, this data should match what it is on the shader code, as expected. Also, remember, there is no transform to the vertices. So we don't do the classical multiplying the mesh vertices by the model to world transform or any of that. It's very simple because we use normalized screen coordinates. So as the data is defined, that's exactly how it's going to be eventually taken by the renderer. No transformations, which makes everything easier to follow. The sticker shader itself, this is how we define the properties of the shader. We define, hey, we're going to use this ACSL, that's where the shader code is. The depth stencil, we disable it. So no depth testing. And here we define a little bit of the blend state, so we can do alpha blending also. And then, of course, the main vertex shader and what is the name of the function for the main pixel shader. And of course, this shader has a draw list called sticker. And of course, here's the shader code, which is very straightforward. The custom data of each sticker is fed on the draw SRG. And of course, which is the texture, that's where we store the texture that needs to be displayed. And for vertex input data, we only need position and UV coordinate, and we take the same and give it back to the, similarly, but of course, interpolated back to the pixel shader. And you can see that the position is basically passed straight. Both UV and position is giving straight to the pixel shader. And in the pixel shader, we just simply sample the texture using the UV, we do a color transformation to transform from this is common stuff in the render that you always have to do to convert, because the rendering assumes that all of the colors before being displayed in the screen, they are in linear RGB, and you want to convert it to sRGB. After you do that conversion, then you get proper color matching at the end. So this is very, as simple as a vertex and pixel shader you can ever write. And then, of course, when you run the editor with the argument where you pass the custom render pipeline, then of course the three in this case, we had if you look at the level that ships with this in GitHub, there are 3 entities, each one which is own sticker component, and this is what you get. Okay, so in this case, so far with using C++, we did custom feature processors, but we were replacing all the main pipeline. Now we're gonna take that same feature processor and we're gonna make it a contributor to them, like another feature of the main pipeline. And this is another place where you need a C++, because you're gonna inject passes into an existing pipeline. And here are all of the APIs that you need to call and in the sequence. And interestingly, you basically query whatever is the current pipeline active. And you need to find, for example, at least one pass that you know that always exists. And this is kind of a gotcha there, because that means that you need to know in advance the probability that a pass called UI pass already exists in the pipeline. And if it exists, then we inject. In this case, I think we are adding the pipeline after, sorry, our pass, our sticker pass is going to be added after the UI pass. All the details are there, and you can see it all in GitHub, how it works. Now, something interesting that changes is that we need to create a sticker pass request asset, where we say, hey, we defines the connections, like exactly how this new pass connects to the existing passes. So all we're saying, hey, we are looking for a pass called UI pass, and we are gonna take whatever is the input-output attachment of the UI pass. That's just a name. You have to know that the UI pass has an attachment with that name. And then if it's there, then we're gonna call that attachment our color output. So finally, just after doing that, connecting all of these dots, eventually you run the editor again, but this time around, you don't customize through the command line argument. You don't customize the render pipeline. You just use the default main pipeline, and the sticker feature processor will find, oh, I found a UI pass. Let me add my sticker pass to that pipeline. And because you still have these 3 entities, each one with a sticker component, then now you have a sticker is a drawing on top of whatever is the main pipeline. Conclusions and what's next. So in terms of the O3DE RPI and the RHI, we're just skimming the surface. And the O3DE graphics APIs are data-driven, yet fully customizable with C++ if required. The O3DE material system is not restricted to support only the main render pipeline. Instead, it is an engine of its own that is ready for creating unique and proprietary materials, render pipelines, and shaders. The main render pipeline is a forward plus PBR pipeline, but should be clear by now that it is straightforward to build a deferred PBR pipeline that can coexist with the main pipeline. And this allows the developer to potentially switch back and forth. So especially for some of you that may be graphics aficionados who like to compare the benefits of a deferred pipeline versus forward plus, you can actually have 2 pipelines running at the same time each one rendering in, let's say, on different billboards side by side, and you can capture all of that data on RenderDoc and compare, how your pipeline performs when you pick the forward plus version versus when you pick the defer version. So there is a lot of flexibility in terms of what you can do with O3DE in terms of customizing the rendering systems. And what's next? Of course, fork O3DE and contribute. If you're interested also in working with OpenXR and virtual reality, you will have to clone the O3DE extra repositories. And here's a link to the documentation, Discord server, and most of you are already part of Discord. So again, thank you for being part of this team. And here's an example of a beautiful scene and put together, in high quality rendering. Thank you.